So in the last video, I introduced you to this proof problem where we were comparing two functions. And we found in the last video that e to the x is greater than 1 plus x for x greater than 0. Now in this video, I want to do another proof problem, but instead we're going to be comparing e to the x with 1 plus x squared over 2. And maybe this might pop out to you that this is the quadratic approximation for e to the x at x is equal to 0. Now, I want you to try to prove this inequality for x values greater than 0. So using the method that we used in the last video, why don't you pause the video and give this a try on your own? All right, assuming that you've given it a go, again, we're going to start this guy off with writing out a start. So here's the start to our proof. And again, we want to define a function that bakes in all the information of this inequality. So our function g of x is going to be defined as e to the x minus this whole quantity. So minus 1 plus x squared over 2. And again, we are interested in x values greater than 0 in analyzing this function here. And real quick, again, this whole function, g of x, is continuous and differentiable for our interval and really for all x values, so we're good there. And again, what do we want to try to do? We want to end up using one of these consequences that come from the mean value theorem in order to prove this inequality. So what we need to do is look at g of 0 first. G of 0, which is e to the 0, minus, and then this quantity 1 plus 0 plus 0. So again, g of 0 is just 0. And now what we're going to do is look at some derivative information, because if we can prove if the derivative is positive, negative, or equal to 0 for x values greater than 0, then we can make a comparison between g of x and g of 0. So let's take the derivative. G prime of x is equal to e to the x, and then minus derivative of 1 is 0, and then derivative of negative x is negative 1, and the derivative of negative x squared over 2 is going to be negative 2x over 2, which is just x minus x. So that's what we have, and now we have to make this call. We have to make this call. For x greater than 0, is this derivative positive, negative, or equal to 0? And how do we find that out? Well, maybe I can rewrite this. And we can use some old information that we found out. I can factor out a negative 1, and we're left with 1 plus x. And if you can remember from the last video, we proved that e to the x is greater than 1 plus x for x greater than 0. So therefore, we're able to say that g prime of x is positive on this interval for x greater than 0. And now, the real crux of the proof, 3 dots for therefore. Therefore, because our derivative is positive, we're able to use this fact up here, which stems from the mean value theorem, saying that our function is increasing. And therefore, g of x for x greater than 0 is going to be greater than g of 0. G of x is going to be greater than g of 0. And then all we have to do is fill back in our information, and we're done. So here we go. We get e to the x minus, and this whole thing, 1 plus x squared over 2. And this is greater than g of 0, which we found to be 0. Let me grab some more space. And then we just add this guy over. So we find, ultimately, that e to the x is greater than 1 plus x squared, 1 plus x, I'm talking too fast, 1 plus x squared over 2. And again, that's for x greater than 0. And we are done. QED. This was to be demonstrated. So there we go. That's our proof. And again, before we leave, I'll toss up a graph here. So these are our two functions, and you can definitely see that e to the x is greater than 1 plus x squared over 2 for for x greater than 0. And you can also see that this is the quadratic approximation for e to the x at x is equal to 0. And we've already touched on quadratic approximations. You could approximate this function here, e to the x, for x values near 0 using this quadratic approximation. And in the previous video, just since we're talking about it, we were comparing it with the linear approximation for e to the x. And I won't spoil it. In a few units, you'll learn a thing about Taylor series, and you'll get some more information on how e to the x compares with its approximations.